Let us discuss about intrinsic semiconductors. As we already discussed that these are pure semiconductor substances, and for pure semiconductors generally fourth group elements, in which generally germanium and silicon are used as pure semiconductors. And write down the band energy gap for silicon. It is delta Eg, it is 1.14 electron volt, and for germanium this forbidden energy gap is 0.7 electron volt. So these energies are generally obtained by electrons in conduction band at room temperature due to their thermal agitation, and electrons will shift to conduction band. So both in germanium and silicon at room temperature, these contain free electrons in conduction band due to which electricity is conducted. We can also write that in solid state of these elements, all atoms form covalent bonds with the neighboring atoms, and as we know that fourth group element are tetravalent atoms, so each atom will form 4 covalent bonds with the 4 neighboring atoms, and we can say each atom behaves as if there are 8 electrons in its valence shell. Reason is, if we just talk about a silicon atom and it is in solid state, it is making 4 covalent bonds with the neighboring 4 silicon atoms. So each silicon will be making 4 covalent bond with the neighboring silicon, and the similar is the state for other silicon also. So corresponding to each silicon in valence shell, there are 8 electrons, and from these valence electrons, some electrons will shift to conduction band at room temperature to conduct electricity. Now we'll discuss in detail about the electricity conduction in pure semiconductors, as well as later on we'll discuss about extrinsic semiconductor, that is how impurity addition will increase conductivity. But let's first continue with the phenomena of conduction in intrinsic conductor only. Let us discuss the bond structure in valence band of a pure semiconductor. As we have discussed that each silicon atom forms 4 covalent bonds with the neighboring silicon atom, and all these bonds are formed by valence electrons. All these covalent bonds we can say exist in valence band, and there is a conduction band, and at room temperature, say an electron from a covalent bond is shifted to the conduction band. There is an electron which is shifted from a covalent bond. The bond is broken due to the energy gained by electron by thermal agitation. So this bond is broken and electron is shifted to conduction band, and as the bond was electrically neutral, due to transfer of an electron deficient place is created, which we term as a hole in valence band, which is equivalent to a positive E charge. Now in this situation, if an electron is transferred from one bond, due to loss of one electron, the silicon atom will hold tightly its other neighboring electrons, or we can say most of these silicon atoms will hold electrons of this zone tightly. So another electron which will shift from covalent bond will be far away from it. Here you can say I am drawing this breaking of covalent bond in the picture near to it, but in practical situation, the gap between these two holes created, or the two bonds which are broken to create electron hole pairs, will be far apart. we can state that in general, out of approximately 10 to power 8 silicon atoms, only one electron hole pair is generated. So you can just keep in mind that the density of electron hole pairs compared to the density of silicon is very lower, approximately 10 to power 8 times lower. So we can state in this situation, whatever density of electron is developed, the same density of holes is also simultaneously created. So we can say in intrinsic semiconductor, free electron density, which is denoted by Ne in conduction band, is equal to concentration of holes, which is denoted by NH in valence band, and it is termed as intrinsic concentration. This given by, you can write Ni is equals to Ne is equals to NH. Ne is the concentration of electrons in the conduction band and NH is the concentration of holes in valence band. And we can state that this intrinsic concentration of electrons and holes depend on temperature, because if temperature of the semiconductor increases, more and more electron hole pair are generated. So we can directly write that Ni depends on temperature as, I'm just directly writing down the expression for Ni dependency on temperature just for your knowledge. It is written as AT cube e to power minus delta Eg by Kt, where A is a constant independent of temperature, T is the absolute temperature, delta Eg is the Fermi energy gap of the semiconductor, and K is the Boltzmann constant. And here AT cube can be written as N0 e to power minus delta Eg by Kt. So this expression gives us an idea about how concentration of charge carriers, electrons and holes depend on temperature.